passport portfolios and the finite effort user, a rare beast, but sustainably managing large numbers of accounts. This is a joint work with Dinei, also at Microsoft, and Paul van Oorschot from Carleton. So when it comes to choosing a password, everybody knows what we should do, right? I mean, everyone knows that passwords should be random and strong, and that you shouldn't reuse them across accounts. But no one does this. No one follows this. I mean, including you, me, and everybody we know. We all ignore it in one way or another. We've all got dodges that include not having things, not committing to memory a large number of random strings. And so what we wanted to look at, why does this prove so difficult? Why is it so hard to do what everybody seems to agree is necessary and important? So let's look at the difficulty of managing not a single password, but a portfolio of passwords, because I don't have one, I don't have one or two that I need to manage. I have on the order of 100 of them, and the same is probably true for an increasing number of people. So if you've got to remember 100 random passwords, so you've got your work email and some banking stuff and Amazon and stuff like that, and then you've got random strings for each of these things. Well, clearly the burden of doing it, if each of those is, let's say, on average log s bits, and I don't want to go too far down the wormhole of how to measure the entropy of passwords, but if each of those was log s bits, clearly you've got at least n times log s bits to remember. But that's not all you have to do. There's another little thing that you've got to do, which actually turns out to be important, which is you have to remember which password goes where. And if you've got n passwords and n accounts, there's an n by n assignment. And the shortest way of compressing that information is log of n factorial bits. So you've got two things to okay. So you've got two things to keep track of. You've got n log s bits, and you've got log of n factorial. So basically, the effort that you have to put in is modeled roughly by this effort of n is equal to n times log s plus log of n factorial. Well, okay, so that's what you've got to do. So let's plug in some numbers on that. Let's suppose you've got 100 accounts, more or less what I have, and you're going to use log s of 40 bits for each of these things. That leaves you with 4,000 bits for the n log s and 524 for the assignment. That's 4,500 random bits, which is just completely infeasible. It's just ridiculous. It's just beyond the capabilities of human memory. Well, of course, nobody does the truly random passwords. We know that users choose things that are, as the last speaker was demonstrating, things that are very far from random. So people have ways of reducing this burden, which is instead of choosing super random stuff, as I've shown there, they resort to, maybe for your top accounts, you use things that are pretty random and strong, and then as it gets down toward things that you are less concerned about, it's Snoopy and words and A, B, C, D, E, F, G, and stuff like that. So you've reduced the burden for your 100 accounts, E times the effort for 100 accounts to be 100 log s plus, and log s can go down as you make passwords weaker and weaker. But key, if you don't reuse passwords, that log of n factorial doesn't go away. And further, these are random bits. It's incompressible. There's no more efficient way than log 2 of n factorial of encoding the information of an n by n assignment. So no matter how weak you choose your passwords, as a matter of fact, let's, as a thought experiment, just set log s equal to 0 there. Let's just forget about it. Let's say you've got a magic way of remembering passwords for 0 effort. You still have 524 random bits to remember, and you can't do it. As a matter of fact, the last talk in this session is on a way to get humans to remember reliably 56 bits. Getting people to do an order of magnitude more than that, it's way too high, even if log s is equal to 0. So what happens is, in addition to using super weak passwords, people have no choice but to basically group and reuse. It's not something, it's not because they're evil, it's basically because it's simply what we're asking them to do is more or less impossible. So people group things that are, and different people have different heuristics, and it's largely a fairly unstudied problem. But it seems that there's no way out. It's not, the question is not, is it a good idea or a bad idea? It seems essentially impossible to avoid. So that puts us into, okay, we now no longer are going to try to do n accounts for n passwords for n different accounts. Let's group accounts into groups and have G distinct passwords for n accounts. And I'll spare you the analysis, but it comes out to be something reminiscent of what we had before, but you now have the effort for a portfolio of n passwords using G distinct passwords will be G times log s plus n of log G. And the important thing here is basically that there's two free parameters, which is log s, your average password strength, and g, which is the number of groups that you're going to use. And the important thing is, if you're going to, you can set, if effort is allowed to go to infinity, well, those can be anything. But if you fix effort and you pull things across, you notice that there's a reciprocal relation between log s, that is your password strength, and g. That is to say, there is a fundamental and inherent trade-off if you're going to have a fixed effort between these two quantities. So let me show that kind of to you graphically. There are many ways to organize a portfolio. If I've got 100 different passwords and my strength and a degree of reuse is as governed by that equation I threw at you, then we can graph in the G, that is number of passwords used to organize your portfolio, and log s, that is password strength plane, we can illustrate this fundamental trade-off for different levels of fixed effort. So when I fix effort, there's essentially this reciprocal relation. Oops, sorry, I didn't mean to do that. There's this reciprocal relation between them. So at, let's say, the green curve there is at 700 bits of effort divided at various for 100 accounts. Where on the far left you have, if I have only one group and I put them all in, I could have a super strong password, which is 700 bits. And then if I divide it into two, it drops down to 300 bits or so. And why is it 300 and not anything else? Well, if you notice that doubling the number of passwords more than halves the password strength. So the trade-off, it's not just reciprocal, it's actually kind of falling slightly faster. So the question here, and what I wanted to illustrate is, the question is not whether strong passwords are better than weak passwords. Yes, of course, they always are. The question is not whether avoiding reuse is a good idea. Yes, of course it is. But there's a fundamental trade-off here if you've got a fixed amount of effort. The question is not, do you want your password to be strong or do you want to avoid reuse? The question is, how are you going to trade off these two relative goods in organizing your portfolio? So which brings us to the what are we actually trying to do? I mean, I understand how to choose a random password and all of that, and mnemonics to help remember it, but that's not the question I have. The question I have is, I've got 100 accounts. How do I manage my overall effort to manage the overall portfolio best? So one thing that you might imagine that you want to do is minimize expected loss. That seems like a very logical thing to do. And just introducing some notation here, I'm going to have the overall loss over the portfolio is L is equal to the sum of PI, which is the probability of compromise of account I, and Li is the loss that I'm going to endure if that account does end up getting compromised. And, well, if I want to minimize that, well, actually we've got very good tools for minimizing these things. You just set the derivative equal to 0, dl with respect to the only independent variable we've got, which is effort. So dl de is equal to 0. And I'm going to make a kind of an assumption that we'll relax later, but let's just suppose password guessing is the only thing we're worried about, and it's the strength of individual accounts that we have to worry about. Well, if the password strength of account I doesn't affect the probability of compromise of account J, which is what happens if things are independent, then things simplify, and you have dpi equal to 0 for all the levels of effort. In other words, if you have a portfolio of passwords and you want to know how strong should each of them be, the correct answer happens at effort equal to infinity. That is, if you've got a curve where putting in more effort reduces the probability of compromise, and you want to reduce the probability of loss, you just set effort equal to infinity, and we're done. So good news. I mean, there's a closed form solution, and it's very simple. The bad news is it's kind of absurd, right? It doesn't really go anywhere. So clearly something wrong is here. Something is very badly wrong. Well, what about the thing being wrong is that, well, nowhere in our objective function did we include effort. And of course, something that cost us nothing, I mean, anything that isn't measured or charged for gets abused. What if instead of minimizing expected loss, we minimize the expected loss plus the effort to reduce that loss? So all I'm going to do is I'm going to change my objective function here, and it's a minor change. Instead of L, as I did before, I'm going to do L plus E. And again, I'm going to assume that password guessing is the only thing I have to worry about, and so the strength of one password doesn't affect the account compromise probability on another. Optimality now happens, again, when I set the objective function with respect to effort equal to 0, blah, blah, blah. And it's almost the same, and I get this derivative, this partial derivative is equal to, the only difference is on the right-hand side. It's not equal to 0, it's equal to minus 1 over Li, which is, it's a minor change when it comes to algebra, but it makes a huge change when it comes to what actually, the actual difference. So if you minimize L, just looking at the curve here of, this is the curve of the probability of harm with respect to effort. You put in more effort, you reduce your probability of harm. If you're minimizing L, the answer is everything is at infinity and all passwords should be, completely as strong as possible, 256 bits or 512 bits or something like that. When you minimize L plus E, things should be related to the reciprocal of the value that you're protecting. In other words, when something has a very high value, then it'll be very far out on the effort curve. But if, remember in this last slide, the derivative was 1 over Li. Well, what happens if Li, the value of the account, is basically 0? Well, the correct answer is that the probability of harm at optimality for the portfolio should be high. In other words, if I'm managing a portfolio and I'm trying to manage my resources across all of the accounts, the right thing to do is not to spend equally on everything. The right thing to do is have some accounts that are extremely weakly protected. So when you, and can I improve the protection of that account by spending more? Yes, I can, but it's suboptimal to do so because you get better return on effort by spending the money on something you care, the effort on something you care more. So when people look at distributions of things like RockU, when you see the top password is ABCDEFG and say, oh my God, what were they thinking? What were they thinking? Well, maybe what they're thinking is that this doesn't really matter that much and they prefer to spend the effort on something else. Okay, so that helps explain why having weak passwords in a portfolio makes a certain amount of sense. So are we done? I mean, it feels like well, not quite. I made a very, a simplifying assumption there that was a little, that password guessing was the only really thing we were worried about. And that's not quite the case. As a matter of fact, it's very far from being the case. Password reuse complicates things, and now a threat to one account or a compromise of one account potentially compromises the others that share the same account. So risk is not independent across accounts, and it doesn't depend only on strength. There are non-strength related risks. So a risk to, if you've got a portfolio of n accounts, the risk to the ith account occurs, depends, of course, on the strength of that account, but also on the effort spent on any other accounts that share the same password, that are in the same group, and also on effort to protect from things like keyloggers and malware and things that are completely unrelated to strength and actually affect the whole portfolio. The bad news here is if we try to do the same optimization trick and blah, 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 we do end up with a system of equations. It is a nonlinear system of equations in terms of n-squared partial derivatives, and it's a little bit intractable. So to make progress on this, what we did is we introduced a segmentation of attack classes into segmenting the attacks that are possible on your account into things that affect all of your accounts. That is a full compromise where you have a keylogger on your machine and it gets everything, it gets all of your accounts and it's unrelated to strength. And then there's the effort that you spend on that would be things like AV and updates and PC hygiene and stuff like that. There's a class of attacks that pertain to the group where the password itself is compromised and therefore anything that shares that password is potentially compromised also. And then there are single account compromises, which are things like session hijacking, which might compromise the account but doesn't compromise what shares the account. Well, it looks, so we end up with a rather more complicated, this is basically the expected loss over the portfolio, summing over these various kinds of attacks, and it gets, I won't lie to you, it gets a little involved, the mathematics gets a little, it's more long than difficult. But the criteria for optimality are, again, when we minimize the objective function, we set these partial derivatives with respect to these different forms of effort equal to 0, and which gives this following system of equations, which again maybe looks a little detailed and there's a bunch of subscripts and I'm not going to go into it. But the important thing here is this is a linear system of equations and we can actually do stuff with it and reason on it. And I'm not going to have time to go into all of the conclusion, all of the analysis, but I'm just going to kind of quickly highlight the conclusions, which is the criteria for optimality. It's not entirely obvious, but the criteria for optimality imply the following things: that if you want to, you divide things into G different groups. And how do you group things? How do you decide which things end up in the same group sharing the same password? Well, if we draw the plane of probability of compromise, that is, PI, and the expected loss over a group account, which is L, then the boundaries between adjacent groups are straight lines that go through the origin in the PL plane. The second insight that comes is that groups that are adjacent to each other should have similar weighted loss. That is, you don't have one group, you don't put all of your really important stuff in one basket and have have most of your potential loss dominated there. So finally, to kind of and as I say, the analysis is a little complicated, but we've kind of tried to reduce it to the kind of the takeaway points, which are, so first of all, random and unique passwords are infeasible for large portfolios. And what we wanted to do here is, instead of asking people to do the impossible, try to take a realistic look at what, stop pretending that what people aren't able to do is actually what they should be doing, and look what are the feasible strategies that we can use to optimize a portfolio realistically. Second, user interest is not to have, is not to minimize loss. It's to minimize loss plus the effort that it takes to reduce that loss. And that difference in objective function just makes the difference between night and day. And it's to minimize that loss over the portfolio. And finally, a realistic analysis, it's easy to come up with a tractable model that includes one subset of attacks, but there's a lot of different attack vectors on credentials. So if you're going to do something realistic, you have to minimize a realistic objective function over a realistic set of attacks. And I think anything that doesn't include the non-strength related threats, such as keylogging and malware, have to be included, which we've done in this model. Finally, the last set of conclusions: a strategy that rules out reuse is suboptimal. It is just, it just implies that your passwords on a finite effort portfolio will be necessarily weak. Similarly, because there's a trade-off, the strategy that rules out weak passwords is suboptimal. And our grouping strategy is, there are a bunch of sort of rules to the grouping strategy. The simplest of them, I guess, is that you group like with like. For example, if you have high-value accounts with low probability of compromise, like banks, it makes more sense that they're together, and low value with high probability of compromise, it makes sense that they would be together. That's it, and I'll take as many questions as the chair sees fit to send my way.
We have time for one or maybe two questions if they're quick. So we'll take one over there and one over here.
So if you have 100 accounts and 100 passwords, and remember the mapping, that was 100 factorial. But if you have 100 accounts and 10 groups, you still have to remember which accounts are in which group.
Yep.
Did you do the analysis on how many?
Yeah, so that's the if I go back, that's the log of where is it? That's this term here. It's G times log S. That's your G passwords, and then you still have to remember N times log G. It's a slightly complicated. Yeah, but it's in there. It's in there. But it's an approximation. There's a third order term that we had to drop off there.
Hi, Rob Johnson from Stony Brook. Really great work. So there's several follow-on questions once you start analyzing password reviews like this, such as, there's rules of thumbs, but did you come up with a polynomial time algorithm to actually, given a set of passwords and account strength and value estimations, actually solve for the cutoffs? What about when you have like a backup password for email that can be used to compromise multiple sites? And what about an online algorithm where you're adding accounts on the fly? So these are all questions.
Guilty as charged. We did not solve those problems. This was, this model is a simplification. There are many things. I could list 10 other flaws in addition to the ones that you name. The claim is not that this is that we give a definitive here, plug in, you know, your 100 account names, and we'll tell you exactly what to do for each of them. The claim is that this better explains why, you know, essentially nobody, including you, me, and everybody in the room, does what we tell people they should be doing, and offers a path forward. But there are, you know, how to choose. Like, one thing that the model does not say is you can. For any given G, there's going to be an optimal strategy. How you should choose the optimal G is not something that we were, you know, that we did. You need. It gets complicated, but many things yet to do. Thank you.
Thank you.